Yes. So as you know, we're using AutoLab, which means that the grading is automatical. And the important thing is that when you submit your code, the value that your function returns is what is asked for. In particular, we have some search problems, and we expect you to return the sequence of moves to get to the from the starting point to the goal as a list of strings. So we have a table, yeah, something like this. And the same goes for the optimization problem. Again, we are providing those files which describe what we're expecting and what you should return. If you're not returning a list, the auto grading will fail and you will get 0 out of 10 or whatever it's the score for each thing. The other thing is for the optimization part, you're required to install CVXPy. There are instructions on the website. Installing on Mac and Linux is fairly easy. On Windows, it requires a little more effort. So if you want to use Windows, you're free to do so. But if you have any problems, please see me tomorrow during office hours. I think that's all I have for.
So what I expect is that most of it is like questions.
Yeah.
And what you do, come to office hours, or and feel free to send me like email questions. These recordings so that it's not
Yeah, definitely.
posted that they're practice.
Yes, there are 2 weeks. The Outlab is still not up. Hopefully, we'll have everything working by tomorrow night. We have some problem with the images of the virtual machine, but we're solving them. So don't worry if you're not on Outlab yet, because no one is there yet.
So I
And
think this is our first time that we're still having the process. I think it's
yeah. Hopefully by tomorrow night everything is okay.
and I think it's before you
Yeah. We'll definitely make an announcement on Piazza once everything is running.
okay. Okay, so where we left off, well, not there, where we had left off last time is on local search. We had done this generative search, and now we're looking at local search, which was this notion of that sometimes you don't really care how you got to a solution. You just care that you have a solution. And in a way of doing that is that you can basically start off with a complete possible solution. It may not be an exact solution. And then you can do moves on that solution and try to get it closer to the ultimate goal that you want. So some of the problems that you might see this far is the 8 queens problem. And as we had talked before, it's this where the queens are allocated on the board such that they're not, and no queen is in the position to attack another queen. And so all you care about is, the positions that you can place the queen there. You don't care about the search that you went through to find out where to put those queens. So one of the boards that could be an initial state could be just a queen in each one of the columns. And then you do moves on that queen in order to find neighbors and then pick, based on some kind of evaluation, which one is the best one of those things, and then explore that as the next neighbor and keep iterating until you can find a solution. So types of things you can see this for, we talked about, is the 8 queens problem, the job shop scheduling problem, circuit design. Again, you don't care how you got to that design as long as it meets all the constraints that you have for that particular chip that you're trying to design. Computer configurations, automatic programming, automatic graph drawing. All these things you just care about the layout more than you care about how you got there. Some of the advantages of this is that it's kind of a really easy thing to do, this local search, only in the sense that it's like you and come up with a quick solution, make some neighbors, and then just sort of walk on this solution. What you're not going to get is optimal solutions necessarily in this. In this case, where you're concerned about the A queen, it only has to be what they call satisfactory result. It either is or is not. You're not looking to optimize the dimension. The local search algorithm can solve such problems by keeping in memory just one current state, so it doesn't have a lot of memory requirements. When do you terminate is always an issue, and we'll see this as we start going through a couple of the local search algorithms. So as I said, one of the advantages is that it's very simple to implement. What's a little bit difficult is understanding what makes better moves in order to starting from an initial state. How do you transform it to neighbors that are likely to be better? That's a little bit of thinking to do. Very little memory, depending on how many states you keep in memory. It's a trivial amount. It's not like you're keeping a whole search tree in. And you can often find reasonable solutions in very large state bases for which systematic algorithms are not suitable. The search trees are just simply too big. You don't have a good way. You don't have good heuristics to know how to search it. So you do use some of these techniques, and you often come up with fairly good solutions, although there are no guarantees. And that's a problem. It depends on what kind of domain you're in. If you need guarantees, you're unlikely to use this approach. So one of the simplest and most well-known, and there are a billion versions of this, but the simplest version is called hill climbing. And the idea of hill climbing is that you create a neighbor, you have an initial state, you create some neighbors, you evaluate those neighbors, and you take the best of those neighbors, and if it's better than where you're at, you use that neighbor, and then you iterate again. And you keep doing that until you get to this sort of local maxima at the top, and that's going to be your best solution that you'll find. So just to follow that through here, say we make the node from the initial state, and then we get the highest value successor of a neighbor. Again, generating the neighbors takes a little science about how you do it, depending on the problem. And then you look at this value, and you say, if the value is less than your current one, meaning that you didn't get any better, then you just return the state of your current one, okay? Otherwise, you make the neighbor your new current one, and then iterate again. And so you can see you're just sort of rising to the top here, all right? And you can also see that there are going to be some problems with that in terms of if you want to find an optimal solution. If you keep finding something better, yes. One of the things they do is, and I was going to talk about this a little bit later, is that if there are time constraints, you will put a limit on the iteration. As I said, there are many different versions of this. This is sort of the boilerplate. But if you have, like, you say, I can only go this much time, you might say, I only do this many iterations. The key point here is also noticing that generating neighbors here, because typically you want to do this fast, better not be an expensive operation. Okay, so some of the problems with hill climbing is, like I said, the local maximum, right? So if you're in a local maximum and your search space looks something like, say, suppose your search, as you're climbing along like this, and your search space goes like this, that's great if this is your ultimate solution, right? But suppose the search space actually kind of goes like this, right? You're never going to find that one. This is your local maximum right here. So that's a problem. If the neighbors that you generate, right, aren't on this up here slope, but they're only within this kind of fallow field here, they'll all look not as good. And if they don't look as good, you're not going to be able to get to the top one. So hill climbing has this problem in that it won't follow this, and that's called the local maxima. Similar kind of thing is on a ridge, where if you're on a ridge, you have a big drop. If you're along the line, you have a big drop off on one side, a big drop off on one side, and the only way you will improve is this line that kind of goes up, which is along the ridge. And your ability to generate a neighbor may not fall on that ridge. And so you're constantly looking at the lower ones, and you never improve. So it's just another manifestation of this sort of local maximum. All right. The other one is a plateau. And that's, again, it's very similar to this, except for it's sort of like you're like this, and then you're like that. Right? And if you're here, your ability to see something over here is not very good. Right? So you're everything you do, you'll be stuck here. All right. So sort of the sacrifices you give up, but it's something to understand. Okay. So you can't get off these things. You have non-optimal results. What do you do? Is there anything you can do to improve this and still use this technique? So one of them is stochastic hill climbing, and this is the idea of using sort of a weighted random choice. So what you do is you have your neighbors, and you apply this evaluation function on it, and you got a value for it. And now you want to say, instead of taking the best one, let's do a random choice, but weight each one of those neighbors based on in accordance to the value being higher. So the higher value ones are more probable to be picked. The lower value ones are less probable to be picked. And then given those weighted choices, you do a random selection from that pool, and you pick it. So you don't always pick the highest one. And what this has some factor to do is that you might be able to sort of jump on different spaces. And if you can jump off that curve, you might be able to get to the better spaces. All right. So you'll see this time and time again as we talk on through this lecture, is that you're looking for techniques to sort of jump out of the rut that you're in. Right. You're in this rut and you're trying to jump out of it. So one of the techniques you'll see is this notion of, all right, I have a bunch of choices. Some of them look better than others, but I'm not going to automatically take the best. I'm going to kind of weight them based on who looks better than not, but then do a random selection and still maybe jump off and get out of my rut. All right. Another way to do it, and this is one that's it kind of goes to your thing about how how long do you do this for, is the first choice hill climbing, and this is the idea of I start off with my initial state, and I just randomly generate a neighbor. And I say, is that better? If it is, great. I'm going to go with that. Do it again. If it's not better, I'm going to throw it away and try it again, and try another random neighbor. And this is almost like this is basically a random walk through the search space. But you're constantly trying to find this better value. This works if you have a really fast-growing, lots of choices. You have a billion choices to do, and you don't know which one to go to. You don't have a strong theory about the search. This is something you might try. Another one is this random restart. So I think you brought up random restarts at one point when you talking about depth search. In that with random restarts, again, what you do is you're going to run, instead of one hill climbing search, you're going to run multiple hill climbing search. But each one is going to start with a different initial state. And in that initial state, you're going to be, again, so instead of just starting, here, right, you could be starting, one could be starting here, another one could be starting up here, one could be starting over here, like here. And so the idea is that you're going to be able to jump these other spots. And then basically you run them in parallel, or you can run them sequentially, and you save the best value. And the best value is going to be the solution. Again, even later on when we come to planning, just a forecast or show you something in the future. Another technique that you'll often see in these kind of search things is what they call portfolio techniques, which is try a bunch of different methods and say the best solution. Sounds pretty routine, but as things become more powerful and computing becomes more powerful, this becomes another kind of option, and that's kind of what random restarts is here too. Okay, so again, we have this notion of local search, and we're trying to figure out how not to get caught in these ruts, these local maximums. All right. So another technique is something called simulated annealing search. Has anybody heard of that before? Okay, great. So simulated annealing is taken from metallurgy, where you try to harden the metal by making it really hot and then cooling it down slowly. And the ideal here, that really where it applies, the analogy, is this notion of cooling gradually, and I'll explain how that applies here. The main idea of this simulated annealing is to have sort of a controlled way of looking at sort of randomly in the search space. Don't just randomly pick all over the place, but have some kind of controlled way and the main idea is that you start off sort of with a large ability to do a wide search across a wide range. But as the search goes on, you narrow down what the ranges in which you can choose random values in that search space are. So as you get closer and closer, if you had a perfectly great schedule that would just bring it all the way down, would converge to 0 at the bottom, you'd have an optimal solution. But you're not likely to do that. Your step function as you reduce the probabilities is going to be in steps, not in this continuous slope. So let's look at the structure of simulated annealing. So really loosely, what you have is you have a initial problem, initial state, so problem, and you have a schedule, and I'll talk a little bit more about what a schedule is. But right now, what a schedule is basically going to determine how much randomness you're going to allow at each step as you go through the search, okay? And this schedule is sort of what corresponds to how fast you would cool the metal if you were doing annealing, okay? So you make the node from the initial state of the problem, and then it says 1 to infinity, but really whatever the steps are in your schedule. It's going to be a function usually that determines how far you want to drop down each iteration, okay? And it says you get the schedule of t, and if you're at the end of your schedule, then you just return whatever your solution is, all right? If not, then you generate all the successors, and then you randomly select the successor of the current, and you determine what's the difference between what's that value, how good is that state, versus what you have now, all right? If that value is better than 0, then you definitely use that one, and you iterate back through. If it's not, now here's where the probability comes into play. If it's not, then you're going to select this, you're going to go ahead and accept this as the next one, based on probability that it's tempered by whatever the value is in t and this difference. All right, and so the idea there is that when it's very large in the beginning of your t here, okay, it's very large, then you're going to have a higher probability of picking these things, but it's also going to be a factor of how much better, how much worse you are than these things. This allows you to jump off those ridges, basically. It allows you to jump off those ridges. And you do this until the end of the schedule, to how quickly it comes down to find the best solution. So here, what you're having here is a very controlled way of looking at kind of local searches around what you've been, rather than just looking at the best. But it starts off with a y that you can pick, and then it gets down narrow and narrow towards the end as you get towards the end of your schedule. So if you wanted to do this very quickly, you'd have a very quick step function down on your schedule. If you wanted to do it slower, then you'd have very small increments until you get kind of hone in on the answer. So all this is just as a way to do a more kind of principled way of looking over that search space. All right. So another one is a beam search. A beam search is something very much like hill climbing, but in hill climbing, you know that you just follow the best. You have one best one. You look for the neighbors, and then you select another best one from the neighbors. Here, what you do, instead of looking at just one, you keep what they call a beam, or a k number of best ones around. So instead of tracking just the one best state, it tracks k best states. You start with k states, and then generate the successors of all k of them. And then of all the successors that you generate, you pick the k best ones and then iterate again. All right? So like hill climbing, there are stochastic forms of beam search, again, to try to get off these local maxima. But it's a little broader than hill climbing because you're not doing just one, now you're doing k, which means that you're looking over a broader part of the search space. Okay. So now similar to beam search, although I think that's kind of a recent acknowledgement. In the past, genetic algorithms, I'm not even sure if people would have called it local search, but I think people now it's pretty reasonably standard people have heard of genetic algorithms, I presume. The idea here is that similar to this notion of having, well, as I had said before, there are stochastic forms of beam search. And in the stochastic forms of beam search, you are, again, weighting of the successors that you pick. Instead of picking just the k-best, you do k samplings of those children where each one of them is weighted by their evaluation function for the probability that you'll choose them to go on to the next generation. So again, this is similar to that here, in that what we're going to do here is, but instead of just having one parent, I'm the guy in beam search or the K1 K search, I'm now going to look at two different parents, and I'm going to have a method for combining their results into the next successors. All right. So it's a strange thing. It's typically applied to models in which we don't have a strong, to a problem in which we don't have a strong model. We don't really understand how they work. So this is a way of exploring it without having a strong theory of the model. So we'll go into this in the details here. The general idea is to find a solution by iteratively selecting the fittest individuals, and you notice that Darwinism at its best, it's evolutionary, we're picking the fittest, and that's not by accident, from a population and breeding them until either a threshold on the iterations of fitness is hit or fitness is hit. So basically either until you find a good enough result, which is the fitness, or if you find a threshold of iterations, you just say, I'm going to run it for as much as I can, and I'll say the best one, and I'll do it for X number of iterations. So let's look more what an iteration looks like. Well, here's the sort of components of that iteration. An individual state, like the initial state or the neighbor state, is represented by a sequence of genes, and this usually requires an encoding. Often you see it in 0 and 1. It will mean finding sort of features that you want to represent, like if it's the 8-queen puzzle, you might say the positions on the board, and you represent that in sort of this binary feature vector. And each one of those things represents the genes, and the whole vector represents the individual. The selection strategy is randomized with the probability of selection in proportion to fitness. So here, fitness becomes the evaluation function, and you run that on that, and it gives you a probability of it being selected to be part of the generation of the next set of children. And then the individual selected for reproduction are randomly paired after they are picked, weighted by their fitness, and then certain genes are crossed over and some are mutated. And so all this sounds like, why would this ever work in a model? Because it seems, sort of like, why couldn't you just take a very holistic answer and then split them up? And so we'll look a little bit more at that splitting them up, and then we'll talk a little bit more about why it actually might work. Right. So here's some steps. So imagine these are the individuals in the population, and these are the feature vectors that represent them. And we run a fitness function on this, and that gives us sort of probabilities of what we want. This is like a 32%, 24, 24, 20%. These are based on these values that it actually gets on the fitness function. And then we say, all right, I want to select some of these from here. I'm going to have a generation, a new population that's going to have 4 new individuals, new generations, right? And that's going to be a function about how many parents I pick and how many children will come from those parents. In this particular version, and there are lots of different versions of genetic algorithms, we are picking 2 sets of parents in this next stage. So we use these things and we randomly sample from these things to pick the 4 parents. And notice that one of them can actually participate in 2 different couples. Right? So this one can participate in this one, and this one is also participating in this one. So they're separate draws. Right? So we end up with these 2 different sets of parents. Right? These are picked from here. These are picked from here. And then what we do is we can either be a random selection about where the cutoffs are, or we can actually assign one based on we know a little bit more about the domain. And then we can say, all right, we're going to pick these cutoffs, and we're going to do a crossover. And if you look at the crossover here, it's like you take this one and this one, you match them up, and this one and this one, and you match them up. All right, and that becomes the children. Now, I know that seems a little like, why would that work, right? And what are the kinds of assumptions you want to make about it? Again, if you don't know a lot about the domain and you don't know a lot about the model, and you have these features, you relatively think that they can be mixed and matched. And what you're looking for is trying to keep sets of features that are together that will have promising outcomes. And so this is a way of searching through that in sort of a kind of a random way, but based on using fitness to somewhat guide you. Again, you do the switch over here, and then just, if this weren't funky enough as it is, right, to get you off a different kind of search space, you have this notion of mutation. Not all things use mutation. It's usually very, very low probability, but it's a way that you just kind of, you just basically pick one of the one of the bits on it, and you flip it, mutate randomly. And again, this is all about jumping at, trying to get outside of those ruts that you might be in if you stayed in and were caught in the local maximum. So here is an algorithm for it. Again, there are many versions of generic algorithms. This one is actually a little different than the one that I showed you in the previous slide, and I'll note that difference in a second. You start off with this new population with this empty set, and then you go and you look for the size of the population that you want to have in the next generation. You randomly select based on those probabilities. In this case, one set of parents, all right, but you're going through each one of these things. And in these parents, you're going to produce one child. In the previous slide, we produced two children, right? So if this were 2, size of this were 2, that would be the same as last slide. Two sets of parents, but not, we're only creating one child, where in the previous slide we created 2 children, right? Then if there's a small random probability, go ahead and do some mutation on that child, okay, which is this step's a little bit earlier. And, well, here we do this reproduce here, which is going to be the crossover that we saw in that previous slide. Sorry, I skipped that. And then we do the mutation here, and add it to the new population, and then the population gets to be new population. And then, until some individual is fit enough, that would be some fitness threshold, we'll stop when we hit that, or enough time or enough iterations has expired, and we'll terminate there. All right. So, the first thing that's, and then return the best information on the population according to the fitness. Wherever you found that was the highest value. So the thing that's you look at this and you think, well, God, how do I know when it's going to stop? How do I know when it's going to get better? What context do I use this? The reality is that people have used these with fairly good fitness fun. They've actually looked at the domain a little bit and applied some machine learning techniques to or search techniques also, to learning better fitness funds, and they've tried different fitness funds. And they've gotten some good results on some big problems. If you're doing this in a real-time setting where you care about how long it takes to compute things, and you're concerned about the quality of the solution that gets returned, this has some benefit in that you usually have some sort of a solution. The disadvantage is that you have no idea how good it's going to be in any time. Right. Yeah. 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 So that TSP is exactly one of the ones. They've done pretty well with that, but no guarantee. For any particular instance, there's no guarantee. But you're right. That's when it works pretty well. Okay. So they've been applied to a wide range of problems, they said. The results are sometimes very good, and the results are sometimes very bad. But they're an easy thing to try. And the hardest thing is trying to figure out what features to encode in that vector. That's a really hard thing to figure out what's a good thing to do. The interesting thing is that I confess I never was really attracted to trying something this way, but I have seen a number of problems which I didn't know how to attack and address this way, and had pretty nice results. Well, like he said, the TSP have done that. They've done them in a lot of scheduling problems too, for example. So what you have, for example, in scheduling problems, what you care about is the order in which the tasks get done on the resources. And people will just generate on the fly very quick orderings on resources. And that'll just be a problem. And then what they do is they just do these kind of quick crossovers to get new orderings on those resources. And they've gotten some very, very good schedules that you really couldn't do in a dynamic way. I mean, if you do it in a heuristic search, you're always caught about whether you pick just one of the first or two time slots. Looking over all the orderings, over all the possible combinations, and all the different number of resources is an expansive state space. So this has been worked very well on that. It's also worked pretty well on some large-scale configuration space where you're trying to find configurations of things that will work together and fit. And you do constraint-based reasoning might be one way to do it, but this is another way that they've applied to one that has a huge number of constraints that interact. So those are some of the local search algorithms, and I just wanted to give you a sense of what those are. We've gone through the generative search, we've gone through the local search, and now I want to go into one last piece of that, which is the adversarial search. Now, I don't want to confuse this with the more complex game theory, which you guys have probably seen in various places. This is really applying to a particular kind of zero-sum search games. By zero-sum search games, I mean that in the end, it always adds up to zero. Somebody loses, somebody wins, or they tie, for example. All right? And as you see in the book, people will complain about it being called zero-sum. Maybe they should call it constant sum, something like that. All right? So here are some of the algorithms that would look like here. One is called the minimax algorithm, and then a kind of more efficient, or potentially more efficient implementation of that, which is called alpha-beta pruning. And then we'll talk about games with chance nodes. And by that, I mean like having to roll a die and seeing how that affects the game and how you might be able to play it. All right? So adversarial search is, of course, everybody loves it because it's like a little game that they can play. I think it's a hell of a lot less interesting than it was when I was doing it 20 years ago, in that people now look at apps on the web all the time, and it's lost its magic. You know, but back when I was doing it, it was like, ooh, wow, this can really play itself. It's really neat. There are competitive multi-agent environments, modeled as games. As I said, there's this notion of game theory that gets into very sophisticated notions of how you can have cooperating or competitive agents, and how you can try to maximize individual utility for each one of them. So what are some of the changes that go from what we were looking at before in all our previous searches, which I would consider a single agent search, to something that's a multi-agent, two-player search? Actions are no longer have predictable outcomes. If I do something, I may know the scope of what you're going to do, but I don't know what action you're going to take if I'm playing you in a game. Uncertainty regarding an opponent and or outcome of actions. That may be the problems that we're going to look at most of the time. We know what the results are of a particular action. So we're not going to be going into the uncertainty of the real world, where you take an action and you don't know what exactly is going to happen. It's a competitive situation. I'm trying to maximize, you're trying to maximize. So there's adversarial there. It's a much larger state space, just simply because now there are multiple different paths that can be taken. It may be the case that there are time limits. You can't think forever. People are waiting for you to make decisions. And we're still assuming, as I said, perfect information. If you take this action, this will occur. Sometimes I refer to that as the closed world assumption. So formalizing the search problem. The first one is that there's an initial state and the initial game board position and player. So that's very much like we had before in our search problem. It's going to be somebody's turn, so that's important to know. Successors, there are operators that are all the legal moves that you can do from a particular game state, given it's your turn. The terminal state, it's not really that it's a goal test. It's more like, all right, how's the game going to end? What are the possible ways the game could end? End in me winning, end in a tie, and then my opponent. A utility function, which is this payoff function, a reward. This is a key idea in that you probably won't be able to search the entire space, but we'll talk about that a little bit more in a game. So you need to estimate what you think getting to a particular board state, what value that represents to you, and how favorable that's going to be. And then a game tree, which is, again, a graph representing all the possible game scenarios. So now it doesn't just have has the decisions of what I can do and also what my opponent can do. So here's a sort of a rough notion of a game tree here for tic-tac-toe. All right. If you think about X from X's perspective, and X is going to want to try to maximize its next move. Whatever the utility it takes in its next move, it wants to maximize that utility. Right? And part of that decision is looking at whatever it does, it wants to minimize whatever damage its opponent can do to it. So that's part of that utility calculation about what's going to be the next move to move. So you're trying to weighing in, all right, this move will put me in an advantageous position, but the opponent may do this, which would put me in a disadvantaged position. So then what is going to be sort of the utility that comes out of that? So if you look at these things, you can look here and you can say, here's my position here. If I can go here, 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 or here. They're all basically, that doesn't mean much. What's the best position I can get here? And then here, when I go down to the max, I'm going to be looking to see what my opponent can do, and back and forward up. And if you do it from the bottom line up here, if you look at it from X's perspective, all the O's win. So that's a -1 utility. That's bad. Here's a tie. That would be a 0 utility here. And here's a +1 here. And that would be good. So you're trying to reason back from these states to what would be the best move for me to take at that position. So what are we searching for? We're trying to construct a strategy or contingent plan rather than a path. We're trying to figure out a set of things that we can do based on and what's the worst thing. If that other guy plays a perfect game, will I be able to maximize what I can do given this other player plays a perfect game? Must take into account all possible moves by the opponent and the representation of a strategy. This is something that we'll see. We'll talk a little bit more and more about. The strategy right now is really represented just by calculating the numbers in the minimax. But as you get to more sophisticated games, you'll start to actually think about strategy. Like, if I play these moves 4 and ahead, that may result in a benefit. Then think of each one just as the benefit of the result of the outcome of the game. Optimal strategy leads to the highest possible guaranteed payoff. All right, so the minimax tree. Generate the whole tree. Label the terminal states with the payoff function. Now, right now, you guys should all your ears should be perking up. Generate the whole tree. You got to be crazy. That's got to be crazy to do that because, even like tic-tac-toe is what 9 factorial states, so it's crazy to be able to do that. But suspend that for a moment, and then we'll go back and address that. All right. Label the terminal states with the payoff function. Basically, look at the boards that were completed and saying what are the values of those boards. Work backwards from the leaves, labeling each state with the best outcome possible for that player, and then construct a strategy by selecting the best move for max. So max is always going to be whoever's turn is next. Right. So the labeling process leads to the minimax decision. The minimax decision being what move to make next. That guarantees maximum payoff, assuming that the opponent is rational. Labeling can be implemented using depth-first search using linear space. And now let's take a look at how that would be computed. All right. So here I am. I'm in the max here. Imagine these are trees. This is the payoff function on the leaf nodes. These numbers have. And now I'm going to say minimize this. What would be the minimum of here? 3 would come up here. Again, the minimizing here would be 2. The minimizing here would be 2. And then if I maximize this, because this is going to be my decision about what I choose to do, 3 is the best move I can make here. This assumes that this guy's going to make all the right moves. The opponent's going to make the right moves, right? So I would pick this move to make. And that would be the minimax decision. Okay. Now I don't know how many games you play, but hardly any. My games never go straight fly. Right? It's way back, larger fly, under fly. So as I said, but seriously, you can't search all the way to the lead. So what you do is you use a cutoff test function. So you go so far down and you apply, you look at those states, and then you apply some evaluation function to those states. And that evaluation function is going to give you an estimate of the utility of that board state, like where it might lead you. Now, finding good evaluation functions is not so easy. But there are some very good ones that people have found. Again, they've tried different things where they've tried some learning techniques, they've done some individual search techniques to try to find better evaluation functions. They'll try different ones. You try to take into account some of the domain model that you understand, and you try to apply that to get a better search function. But they're hard to find sometimes. But that's what you have to use in order to be able to really work in a practical context where the game tree is many, many, many nodes large. So you basically will go down to a certain depth, apply the evaluation functions to those states at that depth, and then just do the minimax as I did before, except for we're now at the bottom. We're just at that place. So it depends very much on how accurate that estimate is for that evaluation function. Okay? So you apply the heuristic and assume that that heuristic represents the payoff and back up using minimax. Okay, so what is an evaluation function? The evaluation function assigns each state to a category and imposes an ordering on the categories. Essentially, you're thinking of this as like, this one is going to be better, this state is going to be better than that state because all the things that could fall out of that, we assume are going to have a higher value. Again, finding and discovering these states are not easy. Some things may come just very easily from understanding the domain, but other ones, people have done a lot of teasing and learning and techniques and tried different ones. And it used to be that a long time ago, people would actually have publications saying, oh, I found a better evaluation function. You're unlikely to see that now, but there was a time when that happened. Some claim that the evaluation should be the measure of the probability of winning. Given that state on the board, what's your probability of winning? And that should be what your evaluation function should return. It's not clear that that's always the case. Whether you're likely to move to lower probability states, it's a big question about the board. I mean, just because it looks really favorable now, it depends on how those things work out. But it's one way to think about it. So some evaluation states that you might think about are, here's some kind of classic ones that they've used before, is a material evaluation. And people who play chess, I'm sure, probably know the material reward, which is just sort of count the pieces for each side and giving a weight. If you have your queen, you're doing better than the team that doesn't have a queen, right? Or the player that doesn't have a queen. And the rook and the 5 and stuff. So that's one. That gives you a sense of what's the powerful state, how powerful a state you are in that part of the board. This is done well, but it didn't really succeed in giving you, the results that some of the better chess playing programs had. And it combined them with a lot of different things. So what properties do we care about in the evaluation function? What do you think? What do you think we would care about in the evaluation function? Any thoughts about that? Yes. Sure, in chess that would be, or depending on the game, with chess that would certainly be right. So that would be a kind of strategy. You could weight the power, by the power of the player in the board, and that could be, that's a great thing to have. What else? Right. How many ways to get to it? That would be one. So outside of chess, what would we think of too? Yeah. It does need to be fast. Exactly. If you're going, the faster it is, depending on how bushy and how wide your tree expands, and how fast your evaluation function determines how far down you can go. And one of the things that you hit, of course, is a horizon effect. Now, if I had just looked 2 dimes deeper, I would have seen that nasty, nasty move, and I would have never gone there. And you're hoping your evaluation function will be able to capture that there's a nasty move too far down that you're not looking at. But if it doesn't, you always have this horizon thing. So having speed on your evaluation function really helps because you might be able to go a little bit deeper. Yeah. That's right. So, which brings up an interesting notion of distance, right? So, what is the distance from winning? That's right. But we don't want to compute too much because then if you compute too much, you get into the problem of having an evaluation function that's too expensive. So that's why you have things like straight line distance in search, things that are very quick to compute. Oh, okay. That's exactly right. So if you have something that looks really good here, you go to a subsequent state down here, and then it looks really bad. You have a very unstable function, and that's going to lead to a lot of problems because it's not going to predict very well, and you're very much subject to that horizon stress. All right. So these are some of the things that you would think, that really matter. The way you look at things, the ordering in which you look at the states and the board also can matter a lot too. And I'll show some examples of that. Give you a little bit more notion here. I just want to give you some more notion about evaluating states in backgammon. Of course, backgammon has a little additional piece to it because it has the roll of the die. But its possible goals are to hit your opponent's slots, right? Reduce the number of lots that are in danger. Build points to block your opponent. Points to remove men from the board, right? So these are all the things that you might consider when you make an evaluation function. Get out of the opponent's home. Don't build high points. Spread the men at home position so it's easier to get off the board for backhand. If you spread them out, then you're not, that way any die roll you throw, more likely to be able to get one off the board. So these are all the things that you might consider, and you might just, linearly add them up to get a utility. You might weight them to get a utility. So there's all these, a number of different ways you can do these. And a lot of them is kind of hunt and peck, see which one's going to work out well. All right. One of the things that has been done, as I've talked about before here, is that you learn the weights of the chess pieces. Use anything from linear regression to hill climbing. You basically play a lot of many different games, and you try to learn the weights that work best in the game. And so this is something that was done for tuning, sort of tuning your automated player. As I said, the hardest thing is to figure out, which features you're going to use to tune and put the weights to. So some of the problems with minimax is that you only go to a uniform depth. It's not like you can look on a horizon that's going deeper in some places and shorter in others. You only look at a uniform depth. And there may be a lot of information in going deeper on certain ones that look more promising. All right. There's the horizon problem, as I said. It overrates sequences of moves that stall some bad outcome. Basically, as you were kind of pointing out, if you think that it's nothing bad's going to happen here, but then something really bad happens later on, this one will look favorable, even though it may be very bad. Does not take into account deviations from guaranteed value. People may not, the games you're playing, somebody may not take the optimal path. So you don't have no notion of the probability of that player, how good you think that player is of taking that path. And it may be that you can get a really good solution by just hoping that they miss that optimal move. And if they do, that might have been the better path to go down. And that might be a riskier play. And does not factor search costs into the process. The only way you factor it into the process is where you choose how far down you go and how fast your evaluation goes. But other than that, it's not this sort of anytime behavior. Okay. So one of the things that minimax may not be appropriate to is exactly this kind of move right here, right? So if you look at these trees here, we're going to minimize the opponent, 99, and we're going to maximize ourselves at 100 here, right? So we end up doing that move over there. But notice that if the opponent doesn't make this move, I get a big utility here, really big utility here, right? And then I would, of course, want to do that move. So maybe I want to take this move because it's just a little bit of risk. But even if I don't, I lost one utility. That may not be bad. I haven't lost the game. I'm pretty much in a similar state that I would be over here. But it's worth this risk to try to tempt them to make the bad move here. And notice that 3 of the 4 moves are really bad moves for them. So minimax doesn't capture that at all. So some of the techniques, as we talked about, is that there's an expense to doing that search. In chess, we can only search full width tree to about 4 levels. That's on a lot of powerful computing. One way we can approach this is, do we really have to look at the entire tree? You know, and still, can we go down deep? I know we've already talked about evaluation functions to be a cutoff value, but can we still, even then, cut off the number of nodes that we look at and be faster about it? And when we say cut out the number of nodes that we look at, we're talking about pruning the search tree. Fortunately, the best move is provably insensitive to certain subtrees. Some subtrees, it may be based on what you've discovered so far in your search. You just don't have to look at them. It doesn't matter. All right. So let's take a look at an example of that. In this example, we're going to use alpha beta pruning, which is this optimization on top of minimax. The goal here is to compute the minimax value of the game tree with minimal exploration. Along current search path, record the best choice for the max. As you're going through your search, you're going to record your the best values you have so far, and use them as thresholds to prune off ones that are going to be exceed. Doesn't matter what they are. Again, I'll show you an example of that. And the best choice for the min value. If any of the new states is known to be worse than the alpha or beta, it can be pruned. We can just not look at it. And I'll show you a tree that shows that. And a simple example of thinking a little bit above just going through the brute computation of figuring out minimax. Okay. So here is another tree, game tree. And what I'm going to show you is how these nodes, you don't even have to look at it. Okay. And first thing we're going to make this assumption about is that we're going to be looking left to right in a depth first search pattern. Right? Left to right, depth first search. So as we go down here, and we're going to come down to here. Okay? And the first thing we say is 41, 11. Think of this as being done recursively, just like depth first search is done. So it's actually going down this, but we're looking at this. So we're now sort of that part of the recursion where we're calculating the value of this node here. And we say 41, 11, what's the minimum of 11? No, we put up 11, right? Okay. Then we're here at the recursion of this node here, and we're looking at this one. We did this one first. We got 9, right? As soon as we got 9 here, we realized that 11, because we've kept this value, 11 is going to be bigger than 9. And 9 is what is going to be the biggest that can come from here, because it's the value. So therefore, 11 is already bigger, so we don't need to look at this. We can just cut that off. All right? And so here we are at 11, and we didn't have to look at this node. We go down over here, and we say 48. We bring up 48 here. And note here, if this was the biggest value that we could get from here, right? I mean, because this is coming up here, this is going to be the min from here. We know that we're maximizing from here, so 48 is going to be the minimum value that we can bring up from here. And then 48 and 11, since I'm doing a min, 11 is going to be here. So now I don't have to look at this, because there's no point in So we have these thresholds that we're maintaining as we search through, and we're using them to prune off nodes that we don't have to look at. So again, here, we've come back now, our search is all the way around here, and we've gotten to here, we brought up 10. And again, we have 10 here. And as we look at this, we're saying, oh, 10 is going to have to come up no matter what. And therefore, I don't really have to look at this value. And because this is 11 here, right, this is the biggest value that's going to come up here. So therefore, I don't need to look at the rest of the tree. And 11 is going to be the point up here. All right? So does everybody see how that sort of works? Now, some of the things that you should be thinking about is, when does this work better than other times? Right? So one of the things that this is it's very order specific. The fact that we went left to right here means that we discovered some of these thresholds earlier than we found them later on in the search. And the earlier you found the entire threshold, the more you can prune. So we'll talk a little bit more about what that means to reorder these things in order that you might be able to do better on average, get more pruning. So first, let's take a little bit look at the at some of the code here for it. This is just a recursive code. You guys should all recognize this as being recursive. Here's with the cutoff state. If there's a cutoff state, meaning that you've hit that level that you've gone to, then you just return the value. And that's sort of the equivalent of being at the leaf and returning the value on. Right? And then for each successor state, get the new value. And this is the equivalent of the max. So the alpha is the max. And then you're going to expand the tree down below it. And the beta is going to be the min. In fact, I think in the version 3 of the textbook, they call it min value and max value, not alpha and beta so much, because they correlate that back to the minimax. Right. So if you see it, if you have the version 3 of this textbook, and you see min and max values, or max values and min values, you realize that they're alpha and beta. So, if alpha is greater than beta, then just return the B. Otherwise, you're going to do this. Otherwise, you're just going to return the A here, back here. And this is the way that we just recurse down, find those values, and decide whether we have to expand the other side or not, based on these thresholds. So the other part of this, of course, is going to be the beta, right? Which is just similar to saying the only difference is really here is the min, where we're going down and we're taking the min, and again, we're passing the bounds of the new successor state, the alpha that was handed down, and the beta value. And it's a really simple implementation, very easy to do it. It'll give you these values back very quickly, and it will cut down on the search tree. In the worst case, though, you won't prune anything, right? Because you won't have discovered. Imagine always increasing values, and you just you won't get to it. In the worst case, you won't prune anything. So what's the effectiveness of alpha beta pruning? Well, it depends on the ordering of successors. That's what I was talking about. With perfect ordering, you can search twice as deep in a given amount of time. The effective branching factor is the square root of Z. So that means you could prune half the tree, basically. And that's great. But you can't ever get that. It's really hard to get that guarantee because you don't know what the right order is. You don't know. You knew that. Probably have the answer. So while perfect orderings cannot be achieved, simple heuristics are very effective. And so there are ways to do orderings on things just based on sort of some rough notion of what you want to make more important. Some of the things you can make more important are if you want to allow if you think something, if you have a sense of a part of the game that you think is more important, like that it's reflective of a particular strategy, then you might make that strategy, those nodes come first in order to then prune down the other ones. But you somehow have to identify those as being part of that strategy. So what about time limit? Well, one of the things we can do is this sort of iterative deepening, and that is iterative deepening like. And that's to do minimax, one level down, 2 levels down, 3 levels down, 4 levels down. Get the best solution you can. And then once you run out of time, if you have some threshold, that's as much as you can do. The disadvantage is that if you had started at 4 down, you might have been able to go deeper, but you started off shorter. So you have a trade-off for guaranteeing yourself a solution with how far you might be able to go. All right. So now we've talked about adversarial search, where it's a 2-player game, but there's no chance. Totally in control of the players. Right? Now let's throw in a little randomness, such as a dice, a die, or dice. So when we add chance nodes to the game tree, we create this new algorithm that we call the Expectiminimax or Expectiminimax algorithm. And this algorithm is just a way of incorporating chance and randomness into the game that you're deciding. So the problem is that the evaluation is now scale dependent. And I'll show you this, and it can be kind of nasty, but you'll see why. And there's even an alpha beta trick for this case. Right? So here's a board that you can imagine that you have your max state, and then you have dice. Basically, you play some randomness in there, and then you do your mid state, and in between whatever they do, there's some randomness, right? And what these things represent is the probability that that's what the dice will have on them, and then what that player can do if they get that randomness, if they get that particular dice. All right? So that's what these levels are showing. It's showing what will happen, randomness if you get 6s, if you get 4 and a 6, all those different things. All right? So given that, what you do is the result is this, instead of taking the min or everything like that, you end up, here's the result. You have the game state here. This is a 2. This is a 3. Here are, suppose these are the 2 probabilities if it's a 2 outcome kind of randomness. And here you can say, well, this is going to be this is going to be 1.8. This is going to be 0.3. If I add them together, I get 2.1. Right? So instead of, now you're adding together what the utility is based on through these chance nodes. All right? And so you get 2.1 here, same thing with here. This is the normal stuff we do, and then we have the chance node, and you go through the chance node, we're again adding up to get to a utility of these that here. We're sort of combining them all the possible things that would happen, all the possible outcomes, and we get the sort of sum of the utility of that node. But notice now, because now we're taking proportions, right, or on these things, we're really vulnerable to scale on our evaluation functions. Right. So in this case here, right, we would, which one of these decisions would we take? Right, we would take, if I was up here, I'm going to take this one, the highest, the highest value, right? So here now we have a scale here, 20, 20, 20, 30, 1, 1, and then 400 and 400 here, right? Notice that this 400 and 400 now, when you do 0.1 here, is going to really lopside, right? Very subject to that scale. And so now, if you look at this, of course, we're going to take this decision. So you have to be really careful with, when you're doing your evaluation functions, that they want them all to be within a similar magnitude. Naturally, these are a little bit different magnitudes, but because it's proportions, you can get very big number differences in different results. Okay. So now let's talk a little bit about where we actually have seen some of these AI playing programming. Of course, you guys all know about Watson, and that's infinitely more sophisticated than any of this. So it's not really as much game playing as it is looking up and understanding the context, what the question is, and going out and finding it. I'm sure we'll talk more about that as part of the natural language processing section of this course. But here we have a computational game, chess, and it made a big, big splash when Deep Blue beat Garry Kasparov, who was the champion then. And the interesting thing about it, of course, is that, just as a sideline, is people said a computer program would never win a chess game. And they started to portray chess as, if you can win a chess game, then you have a cognitive computer. And then it beat Kasparov. And then they decided, oh, that's just a computational task. Of course, it can do that. It's not cognitive at all. So I actually think that I'll be honest, I think the former threshold of if it won in chess, it's cognitive, was a poor threshold. But it was interesting how people were willing to accept that initially. One of the things, I guess, even one more digression, if you allow me. One of the things that we talked about, that Zico talked about early on, is he talked about AI as an optimization task. And where there's a little bit of difference is there is actually a whole segment of AI which is not about optimization, which is about cognitive architectures. It's about semantic understanding. It's symbolic reasoning. It's a little bit different. It has been suppressed a lot over the years because of the successes of the quantitative side of AI. But people are rapidly coming back to the other side because as successful as the quantitative side has been, it's also been limited in what it can show as results. And the greater scheme of wanting to show a cognitive agent hasn't, also like the symbolic logic, which was first, didn't suddenly come out. It hasn't arrived. So whatever seems to lose momentum sort of loses a little bit, and then something else comes back into vogue. Anyhow, this continues on. In my mind, we have a huge, huge gap to cross to get anything close to a cognitive agent. But I do think that with the advances in robotics, given that my home institute is RI, I have to put a plug in for it. Given that we now have situated intelligence that has to deal with real-world environments and real-world perception, real-world tactile understanding, I think that that's a good first step to getting there. Anyhow, so for Deep Blue, this was a big deal that it won. It won a had a six-game match, had a parallel computer with 32 power PCs, which seems like nothing now, but back then that was like the big chip. And it could search a billion positions per move, reaching depths of 14, which seems really, really deep when you think about the computational size of a chess game, but still it's a drop in the ocean compared to the total number of states. So the reality is that alpha beta was improved with what they called sort of like this forward referencing. They said, oh, this strategy looks good. So because this strategy looks good, we're going to associate these states with that strategy, and we're going to look at them first. And so by looking at them first, we can prune more. And so that was one thing they did. The other thing they did, and this was a very, very big factor, is they didn't run alpha beta pruning on all the time during the game. So they had a big library of open game moves. How to get to control the center of the board, as you're saying. How to do these things. So they had a big library of these opening sets, and they had a big library of closing sets. And closing sets is a little bit harder because you don't start with the same state every time. But you would pattern match and get to those states. And when you would get into those positions that they could match up, they would play those rote games at that point, and not play this kind of expected, this minimax or alpha beta pruning type game. So it was only in the middle that you played those games, and that made a big, 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 big difference in the ability of these programs to, one, perform within the time limit, and two, the outcomes were much more favorable. So checkers, and like Zico said, one of the first AI programs was Samuel's checkers program. It's not the state of the art, as you might imagine. It's from 1952. But it's still interesting. It's interesting that it uses the expert level performance using nothing. I don't even think you guys even, I think a squirrel on a wheel might do better, okay? And nothing in the memory either. You know, very few, very small memory. As you can imagine, things got better. And Chinook was actually a very high-performing program. It won the 1992 U.S. Open and first challenge for a world championship. Lost a match against Tinsley. This guy was amazing. He's like idiot savant about this. I mean, he just was unbelievable. Who had only lost in 3 games before. Became world champion in 1994, and it used alpha beta search combined with a database of 444 billion positions with 8 pieces of less on the board. So again, it had this cache of good places to go to. Again, it really benefited from that. But this again performed very, very well, and the fact that it performed very, very well was the first thing that people could say when they said, well, that's not intelligent. You know, but before that, everybody thought, oh, it performed well, it's really intelligent. Backgammon, TD Backgammon by Tsaro. This was a kind of a, you know, people thought backgammon because of its because of chance and things, it would be a hard thing to do well, and yet it did very, very well. It ranked among the top 3 players in the world, and the key thing about this thing is this neural network technique for developing remarkable heuristic evaluators. It had this, you know, we haven't talked about neural networks, but a neural network is a sort of self-attenuating process to decide what weights to assign to things. And you just play over and over and over again, and you can assume these weights. Now, it assumes a regularity, as you were like talking about. If you don't have regularity, then those things will bounce back and forth, and you won't get any kind of convergence on the weight. But if you get a convergence on this weight, then you get a really, for some, I don't know why, but it found a beautiful, beautiful evaluation function. And that made this program play very, very well. So by playing lots of different programs, using a neural net to apply to that thing, to try to figure out the weights to apply in the evaluation function, it came up with a really nice set. So it's this combination of different AI techniques in order to come up with a really high-performing game. So this used the Expectiminimax search, and notice, it didn't go very deep. It only went 2 or 3 down. That's hardly anywhere, right? But remember, this is with those chance applies in there too, for the dice. This just shows you how amazing this thing was. This evaluation function was. I mean, really amazing. Just that deep, you could already, which is hardly anywhere, you know, it could make a really good guess about what the next thing to do. So it's pretty amazing that way. Another game is Bridge, and I confess I never understood Bridge, so I'm not great at this. One of the interesting things about Bridge is that Bridge is a game where it's only partially observable. You don't know what your opponent has. Right? All these other games we've talked about, they're fully observable. Here, you don't know what cards are being held. So it was a little bit different here. Ginsburg is, by the way, does lots of different things. He does a lot of optimization processes too, but this is he just did it on the side time. He's an entrepreneurial type guy too. He won a computer bridge. This program won the computer bridge championship. Finished 12th in the field of 35 at 1998 World Championships. It examines how each choice works for a random sample of up to 10 million possible arrangements of the hidden cards. So he's making guesses. You can imagine how extreme that is. And then he used explanation-based generalization to compute and cache general rules for optimal play in various cases of situations. So the idea is here is that he then coupled this kind of look ahead about what he thinks they had with something where you reify, and by reify I mean you look at all these examples and then you draw from that, from the explanation of that, something, rules that you can then apply categorically, right? So rather than looking for the instance of it. So these rules may be overcasting. They may say this is always going to be the case. It might be that 20% of the time that's not going to be the case. So you have to be careful about how you apply rules. But if the rules are very good, they're, one, incredibly efficient and fast to apply, and two, they provide a strong model for whatever the problem is that you're doing. So anyhow, this was very successful. Another way of these games learning success. But you notice the ones that are all successful are all these kind of bare techniques that I suggested to you, coupled with some techniques for learning evaluation functions, coupled with cache states and rote ways of playing things after you get those things. So by themselves, they weren't successful. It's all this kind of coupling together. Okay, so I'll stop here. It's 2:51 now, so I'm a minute late. And we'll pick up on constraint satisfaction problems next week. And again, go to the website, get the assignments, and get the templates for the optimization and the search problems. If you have any questions, I think posting Piazza is the best way to do it. And I highly, highly recommend start early. I know every teacher says that, but I'll say it too. All right? Start early. Okay.